So we can start now if you allow us.
Yeah, no problem. No problem.
Yeah.
Anushri?
Yes, ma'am.
Yeah, bas एक minute. Good afternoon, Professor Sanjeev.
Yeah. Good afternoon.
Yeah, I
Yeah.
just wanted to welcome you and wanted to inform I had an urgent meeting at the institute level. So my team will be there to handle it. I'll try to log in at the time when
No issue at all. No issue at all.
they will be there to handle, sir. In case any problem, you can just tell the host.
Yeah, sure.
Thank you, sir.
No issue. Yeah, please carry on.
Anushri, you can start.
Yes, ma'am. Good afternoon, everyone. Myself, Anushri from Indira Gandhi Delhi Technical University for Women, will be hosting you in this session. For this session, we have Professor Sanjeev Malik from Department of Mathematics, IIT Roorkee with us. Professor Malik has worked as postdoctoral fellow in AVIRES laboratory at Department of Mathematics and Computer Science, University of Udine, Italy. He has received his PhD degree in mathematics from IIT Roorkee. Professor Malik has completed his MSc and BSc from IIT Roorkee and CCS University, Meerut respectively. He is co-author in 2 book chapters and author of multiple international journals and conferences. He is also a reviewer for more than 5 reputed international journals. His area of interest includes mathematical image processing, machine learning, computer vision, pattern recognition, and soft computing. He has been awarded as Outstanding Teacher Award for undergraduate category by IIT Roorkee in the year 2019. Multiple research projects funded by ISRO, SERB, and DST agencies are ongoing under his guidance. Dr. Malik is an active member of SIAM, IEEE Computer Society, ACEE, International Association of Pattern Recognition, and IACSIT. Dr. Malik has also a part of organizing committee of various international conferences. Professor Malik has also developed 4 NAPTEL courses. So I request Professor Malik to address our attendees.
Yeah, thank you, Professor Anusri, for nice introduction. And thank you for inviting me for this talk. I hope I am clearly audible.
Yes, sir, you are audible.
Yeah, thank you. Thank you very much. So in this talk, I will talk about manifold learning. So what is happening? Usually whoever is working in the area of machine learning or pattern recognition, we used to apply this manifold learning whenever we are going for some real life problem. But what is manifold learning? That is not known to many of us. So I will try to keep a simple introduction of manifold learning because certainly as machine learning is very popular topic nowadays, and we are now jumping in the era of deep learning. We are doing a lot of work. This manifold learning is something which can be utilized in case of deep learning also. So what is the objective of manifold learning? That is, I have written here in a very simple word. We need to find out meaningful low dimensional structure hidden in high dimensional data. So basic objective is to reduce the dimension of the data. And here dimension means number of features. So to reduce the number of features of the data without affecting the quality of the data. Okay. So without losing much information. So that is the objective of manifold learning. So with this brief idea of my talk, let me start, and you can ask any question wherever you have any query. Please feel free about it. Okay, I will try to answer your question up to an extent whatever I can give. Okay, so please ask, don't hesitate. You can write in chat box, and if possible you can unmute and you can ask me. So it can be a two-way communication instead of one side lecture. Okay, so Now what we are having when we talk about real life problems, many of the machine learning problems involve thousands or even millions of features. And some of the example of those kind of data is documents where you are having thousands of words, millions of diagrams, images where each pixel is a feature, if we see in a direct way. So if you are taking a simple 500 by 500 image, so what is happening? You are having somewhere 25 into 10 raised to power 4. Okay, 2.5 lakhs features for a small image of 500 by 500 size. And when we talk about videos are sequence of frames, a sequence of images. And let us say we are having a not a very good quality video, but somewhat manageable quality. And there we are having, let us say 10 frame per second, which is not very good in terms of high speed imaging, but still, and each image is having a resolution of, let us say, 1000 by 1000 means size of image. So it will become 1000 into 1000 into 10, this much data per second, and then it will depend on the length of the video. If it is of, let us say, 500 seconds, you have to multiply with 500 also. So you can see we are having billions or millions or billions of features for a simple video data. And then again, very important topic where nowadays machine learning is or deep learning is quite popular, and that is genomics, where you are having thousands of gene, millions of DNA polymorphism. You have to learn the protein structure, you have to analyze all those, and there again you are having millions of features in your data, especially in bioinformatics data. So now when you are doing this large feature data set, when you are playing with those features, you are applying machine learning algorithm. What is happening that it will make training extremely slow, because you know that running time complexity will depend on the number of samples in your data as well as number of features, means dimension of the data. And since you are measuring the running time complexity in terms of dimension of data, if dimension is large, certainly you will be having slow or poor running time complexity. So it is one of the thing, but there are many redundant features also. And those redundant features, what will do? They will make your classification or whatever machine learning tool you are using, and they make it very difficult or very hard to learn. Sometimes it will affect your accuracy also. So all those issues comes under a particular theme, which I will say curse of dimensionality. So now what is the solution? So solution is, there are algorithms which can reduce the number of features in a large way. And then whatever problem you are having difficult to solve, it can be done very easily using any machine learning algorithm. Okay, so that is one thing where we can reduce, we can remove the, or we can eliminate the redundant features from our data. The second thing is, it will speed up the training, and hence you are having scalable algorithm. And the more best thing is, when your data is having, let us say, 10 dimension, 20 or 100 dimension, you cannot visualize the data, you cannot plot it using any plotting functionality. But if it is in 2D or let us say 3D, you can plot. And then you can visually analyze your patterns. You can analyze whether the data is linearly separable or not, what kind of clustering I am having in my data. All those aspects you can visualize there, or you can analyze there. So in that way, this is the motivation why we are going for dimension reduction. So let me take very basic example, a toy example. Let me take a toy example. And in toy example, what you are having? You are having data of 10 cities. And those 10 cities are having 7-dimensional data. So each feature vector corresponding to each city, I am having 10 feature vectors, 10 samples in my data. There are 7 features. One is education, job opportunity, safety, air quality, entertainment, connectivity, and foods. Now, if I simply ask you which feature is not useful for me in this data, suppose my objective is to classify all these 10 cities into 2 classes. One class is good city for living. Based on these numbers, this data which I have rated each city against each parameter on a 10-point scale, higher the value, the better the facility. So I have to classify my data into 2 classes, all these 10 cities, good city for living and not good city for living. Okay. So which particular feature out of these 7 features is not useful in classification? Or we can say which is redundant here. Any idea? You can write in chat box, chat window. Which one is not useful? Yeah, entertainment. So you can see entertainment is not useful because it is having same value for all 10 cities. So whether you include it or don't include it, still you don't have any effect on the classification accuracy. So why to include it? Why to increase the data size? So again, if I ask you, okay, tell me 2 more features. 2 more features which I can eliminate if I need have 4-dimensional data only. So next 2 features, what you will consider? Food, wonderful. And then, yes, food is okay. And then, safety, yeah, wonderful. Why we are choosing them? Because these columns are having least variation, means less variation. They don't have much variation. So in that way, I can say which column is more useful, more informative for classification. The column which is having more variation. Okay. And in that way, I can suppose I want to come from 7-dimension to 4-dimension. I will choose 4-dimension of my data in which the data is having the maximum variation. Okay. Maximum variability. Now here we are directly removing these, but that is not an idea. Means you are having, let us say, n number of features. Okay. And then out of those n, you select any m. Okay. No, we can't do this. Okay. Because if when you are having, let us say 2-dimensional data, let me take a very simple example here. And let us say these are my data points. So now if I ask you, if this is x1, this is x2, and I ask you, suppose I want to reduce this data into 1D. Okay. Here I am having 2-dimensional data, 2 features. One is x1, another one is x2, and then these coordinate values are the feature values here for all these 6 points I have plotted, 6 rows. Now, which is the most informative direction if I want to reduce this data into 1D? Yeah, anybody can write in chat window. X1 or X2 or something else. Yeah, so let me write, no issue. So here you are having this direction. Okay, because your data is having maximum variation in this direction. So if you project all these data point onto this line, then your data will be having one-dimensional representation. So let us say from this two-dimensional data, I am generating a 1D data, which is, let us say, feature name is Y now. And now the direction of Y will be the direction of this line. Now, what is Y? Y equals to x1 or y equals to x2? No. Y is a linear combination of x1 and x2. Sorry. Yeah. So I can write here. Y is a linear combination of x1 and x2, where alpha and beta are some coefficient. So if alpha is 0, y will become, and beta is 1, then y will become x2. If beta is 0, alpha is 1. In that way, y direction of y will be the horizontal direction. But now it is a linear combination of x1 and x2, means it is an inclined line between x1 and horizontal and vertical axis. Now, how to find this alpha 1 and this alpha and beta? That is the objective. Once I will be having best alpha and beta for all data points, there will be a unique value of alpha and beta, this pair. So if I find able to find it, I will be able to reduce from two-dimensional data to one-dimensional data. Or in other way, what I can say, suppose yeah, I am coming to this, Sachin. I am coming to this. Okay. So suppose you are having n-dimensional data and your feature in n-dimensional is x1, x2, xn. And you want to reduce it to a m-dimensional data. Let us say new features will be y1, y2, yn. Okay, so I am going n-dimensional data to m-dimension, and where m is very less than n. Let us say n is 1000 and m is 100 or 20 or 5, whatever. So how to get from this n-dimensional vector? It is a vector of size n by 1. It is a vector of size m by 1, m number of row and 1 column. So what I need to do, I have to perform some multiplication on this column. And multiplication on this column means I need to perform multiplication of a m by n matrix. Let us say this matrix is alpha 1 1, alpha 1 2, alpha 1 n, beta alpha 2 1, alpha 2 2, alpha 2 n. And in that way, you will be having alpha m1, alpha m2, alpha mn. So now if I am able to find out from the given data, if I am able to find out this particular matrix, I can reduce the dimension of my data. Okay. It is a matrix and it is a linear transformation, means I am projecting my n-dimensional feature vector to a m-dimensional space. This is the meaning. Okay. So, and this process is called, when it is linear and you are doing it in some way, there is a technique which is called PCA, Principal Component Analysis. Might be many of you have heard about this technique whenever you are going through some literature in machine learning, because it is very old and very popular technique and very basic one. So PCA objective is to find out such a matrix. Now, how to find out? What is the concept behind it? The concept is very simple. So before going to that concept, I need to introduce you only two things. One is the concept of covariance matrix. So what we mean by covariance matrix of the data? So suppose you are having a data set where you are having information of the employee in a company. Let us say you are having age, let us say salary, and let us say expenditure. So this is a three-dimensional data where features are age, salary, and expenditure. And in that way, you are having this E1, E2, let us say n number of employees. Okay. So in that way, this data matrix is nothing n number of row and 3 number of columns. Let us say age I am denoting by x1, salary by x2, and expenditure by x3. Okay. Now what will happen? What each column, each a particular feature value, means if I want to say the column corresponding to age will be having n entries, and that is having the age of n employees of that company. Similarly, x2 is having salary and x3 is having expenditure information. Now, out of these three, which column is more useful? If I need to classify these employee in certain classes, the column which is having more variation or more standard deviation. Now, there is a concept of uh, covariance. Okay. Now, what we mean by covariance between, let us say you are having only two columns, x1 and x2. Okay. So covariance between x1 and x2 is nothing, just it will be a scalar, and that will be the dot product of the column vectors x1 and x2. And what sort of column vector? By d mean that. D mean means you calculate the mean of this age column, subtract that from each entry, so that the mean of column x1 becomes 0, mean of column x2 becomes 0. Now you are having this n-dimensional vector. You take the dot product, element-wise product, dot product of those. Okay. And once you take the dot product of those two vectors, you will get a number divided by the n, and that will be the covariance. Now this covariance may be positive, negative, or 0. If covariance is positive, means if one particular feature is increasing the value, the numbers, another one is also increasing. Means you are having variation or change in the data for those two features in the same direction. If age is increasing, salary is also increasing if covariance is positive. If covariance is negative, you are having change in opposite direction. If one feature is increasing, another one is decreasing. And if covariance is 0 between any two pair of column, then I will say these two columns or these two features are independent. There is no correlation between them. So one can say correlation also. Okay. More better word is correlation for this. So that is correlation between x1 and x2. So let me say correlation. Or in some there one can write covariance also. And let us say it is denoted by sigma x1, x2. Or let us say in short, I will write sigma 1, 2. Similarly, I can have a correlation between age and expenditure. So that I will write, let us say sigma 1, 3. Correlation between salary and expenditure, that will be sigma 2, 3. And you know, whatever correlation I am having between age and salary, same will be having between salary and age. So sigma 1, 2 equals to sigma 2, 1. Sigma 1, 3 equals to sigma 3, 1. And sigma 2, 3 equals to sigma 3, 2. Now, what is covariance matrix? So, if you are having n-dimensional data, covariance matrix is a n by n symmetric matrix. Not only symmetric, in fact, positive definite also. So like here you are having three-dimensional data where dimensions are age, salary and expenditure. So I will be having a 3 by 3 matrix, which will be the covariance matrix of this data. Let me represent by sigma. And now these entries, this first entry will be the variance of this column, x1. Whatever variance of this column, that will be this entry. The second diagonal entry means this is the main diagonal of the matrix. So second diagonal entry is variance of second column. And similarly, this one will be the variance of third column. So here you will be having variances, and then you will be having this entry is nothing covariance between first and second feature. This entry is variance correlation between first and third feature, and so on. Again, it will be sigma 1 2, sigma 2 3, sigma 1 3, sigma 2 3. So in that way, this matrix is called covariance matrix. Now, when you are having a square matrix, corresponding to each square matrix, we are having some eigenvalues and eigenvectors. So now what is the meaning of those eigenvalues and eigenvectors? Because for PCA or for any other algorithm, we will make use of eigenvalues and eigenvectors. And I think all of you have gone through this during your graduation first year. So just let me just give you a brief glimpse how to see them, because they are very important in any machine learning technique. Okay, one second. Suppose I am having this x-axis, y-axis, and I am having a vector. Let me write 2i, and this vector is x, 2i plus 3j. This vector is 2i plus 3j. Or in more proper way, I will write it 2, 3 as a column vector, where first element is the component along x-axis, second is component along y-axis. So if I see this vector, I want to represent it in this two-dimensional space. So this vector is something like this. So this is the point 2, 3. Okay, this is the origin, and this is the length of the vector, and this is the direction of the vector, which this vector is making with x-axis, and that is given by tan inverse 3 by 2. This theta, this is the theta angle, theta equals to this. Now what will happen if I multiply this vector with a matrix? So let me take a matrix A equals to 2, 1, 1, 2. Now if I hit this matrix on the vector x, which is 2, 3, so it means you are pre-multiplying this matrix with the vector 2, 3. Once you will do it, what will happen? You know, matrix multiplication, it will become 7, 8. So 7, 8 will be somewhere here. So my new vector will become okay. So this is y. So what I want to say, whenever a matrix will hit a vector, you will take the product of a matrix with a vector. The vector will scale. It may enlarge or it may stretch, means it may compress. And the same time, its direction will also change. So direction will also change, like here now direction becomes something tan inverse 8 by 7 here. However, for a given matrix, there are some vectors for each matrix, square matrix, there are certain vectors. If you hit those matrices onto those particular vectors, they will not change their direction. Okay, like here. So for example, you are having a vector, let us say 1, 1. Now you hit this matrix say on this 1, 1. So I will be having 2, 1, 1, 2, and then 1, 1. So it will become 3, 3. And now whatever direction of 1, 1, the same direction of 3, 3, because it will become 3 times 1, 1. So what I want to say, Ax will become 3 times x. And now this will become 3, 3. So here you can say very clearly that direction is not changing. So for a given square matrix, you are having certain this kind of vector. Okay. And these vectors are called eigenvectors. So now what kind of relations we are seeing by eigenvectors? If you multiply A with that vector, it is coming some scalar times, which is the scaling factor, into that vector. So in general, I can write this relation as Ax equals to lambda x. So for any square matrix A, a non-zero vector x is called an eigenvector of A if Ax equals to lambda x. And this lambda is a scalar called the eigenvalue. Eigenvalue of the matrix A. Okay. So for example, you just see this data. So here I am having thousands of points in two-dimensional space. Each dot is a point, data point. It is a two-dimensional data. There are two features, x1 and x2. The covariance matrix of this data is given by this matrix 2, 2, 2, 3. It means the variance along x1 axis is 2, the variance along x2 axis is 3, and then 2 is the correlation or covariance between x1 and x2. And the mean of this data will be somewhere at the point 2, 3, and this point 2, 3 will be somewhere 2 and 3, somewhere here. Okay, so there will be the centroid of the data. Now, if I want to ask you, I want to reduce this data into 1D, one-dimensional data. So, which is the direction in which data is having the maximum variation? In which direction this data is having maximum variation? In x1 direction or x2 direction, or there is something else?
In the x1 direction.
X1 direction, is it? Data is having maximum variation along x1 or x2 or something else. If I say you that in this direction, yes or no? It is having variation more than x1 direction, yes or okay? Yeah. So it is having maximum variation in the direction of this line. Now, how to find out the direction of this line? This direction is nothing just the eigenvector of this matrix corresponding to principal eigenvalue. Principal eigenvalue means largest eigenvalue. Means in this direction. And what is this direction? This is the eigenvector corresponding to principal eigenvalue. So if I calculate the eigenvalue of this matrix, they are coming 0.43 and 4.56. This is the vector corresponding to eigenvalue 0.43, and this is the eigenvector corresponding to eigenvalue 4.56. So which is the principal eigenvector of this data? This one, because it is corresponding to principal eigenvalue. Principal eigenvalue means the biggest eigenvalue. And this data is given by this, this direction is given by this green line. So this is the direction of principal component. Okay. And once you project all your data points onto this line, your data will become one dimensional, because what kind of data points you are having? You are having feature x1 and x2. So they will be having some value, let us say alpha, not alpha, alpha will be confusing. Let us say x11, x12, x21, x22, x31, x32. In that way, you are having xn1, xn2, these endpoints. So now you want to make it one dimensional data. Let us say that is y, you are representing that feature by y. So what will be y for first? It will be 0.61 x11 plus 0.78 x12. That is corresponding to first feature vector. Similarly, for second one, 0.61 x21 plus 0.78. 0.61 and 0.78 I am taking from the elements of principal eigenvector into x22. In that way, you will be having 0.61 xn1 plus 0.78 xn2. In that way, you can go ahead and you can get one-dimensional data. So for example, here you are having this two-dimensional data, and after applying PCA, you are having this one-dimensional representation. So in this direction, this data is having maximum variation, and I have project all data points onto this line to make it 1D data. Okay, so in short, what we can say, how you will apply PCA? Suppose you are having 100-dimensional data. Your first step is calculate covariance matrix. So you will be having a 100 by 100 matrix, which will be having eigenvalue, let us say lambda 1, lambda 2, up to lambda 100. And these eigenvalue, let us say in sorted order. Lambda 1 is the biggest, lambda 2 in second, and so on. And lambda 100 the smallest one. Now suppose I want to reduce this 100-dimensional data to 20-dimensional data. So what I will do? I will calculate eigenvector corresponding to top 20 eigenvalues. Okay, 20 largest eigenvalues, x1, x2, x20, let us say, are those eigenvectors. Now each eigenvector is 100-dimensional vector because it is an eigenvector of 100 by 100 matrix. What you do, you make a matrix like this. You write x1 first as a first row of this. Second row of this matrix, the second eigenvector, and 20th row is the 20th eigenvector. Okay. Now you are having this 20 by 100 matrix. You are having this 20 by 100 matrix, and this is your PCA matrix. This is the PCA matrix, because whenever you will apply a 100-dimensional vector to this matrix, you will get a 20-dimensional vector. And that you can do for each feature vector of your data, and your new data will be of 20 dimension. And this is the PCA. Okay. However, there are problems with PCA. Let me show you some problem with just a small demonstration. So let me go to my Jupyter Lab notebook, and let me show you just first a very simple thing. So this is just a basic implementation of PCA. In first cell, I am importing some libraries. So no problem, whoever is not familiar with Python, it is not very difficult. Okay, you can find these codes. I will share one GitHub or Google Drive link. There you can find these codes. and you can learn these codes. These are very easy. In the second one, I am creating some random points. Okay, 200 points, and it is two-dimensional, means in 2D plane, and I am plotting those points. So you can see these are my 200 points. Now if I ask you, if I want to make it one-dimensional, this data, so what will be the dimension? Horizontal, vertical, or something oblique line? So a line you will be having if you can follow my cursor in this direction. So that you can directly find out using the PCA library of Python. Although even I am calculating the covariance matrix, I am printing it. So this is the covariance matrix. I am calculating the eigenvalue and eigenvectors. I am printing them. And then I am taking the principal eigenvector and I am applying here. And finally, you will be having your one-dimensional representation of this data in this way. Okay, so yellow one is the new 1D data. Okay. So this is your PCA. So you can see here original shape is 200 points from two-dimensional, transform shape is 200 points from 1D. So now instead of using the original two-dimensional data, one can use this one-dimensional data. If you see on some, let us say, on some real data, so it is a handwritten digit data set where you are having 8 by 8 images of handwritten digits from 0 to 9. So total 10 number of classes are there. And I am just showing you two classes here. All images, those are having either 6 or 9. And this is a supervised learning data. So I know the class information also. So you can see total I am having 361 images, each one of size 64. Each one of size 64. Now what I will do, I will apply PCA because now each image is 8 by 8. So there are 64 pixels. So 64 dimensional data. Now look, just by applying the PCA utility, PCA class of sklearn.decomposition, which is scikit-learn library from the Python, I am reducing this dimension from 64 to 2. Here number of components is how many PCA features you want to have. And just you have to apply these 3 lines for any sort of data. So you can see my original data is total 361 samples from 64 dimension. Now it is becoming the same number of samples but 2 dimension. Let me plot some of them. So you can see here 6 and 9. So you can see all 6 are coming in left side, 9 are coming in right side. So in this data set, handwritten digit data set, 6 and 9 are having separate cluster. One can say they are having linear separability. Means you can separate them just by a line. Even in 2D. Even in 2D. Original data is 64 dimension. But by reducing the dimension to 2, I can analyze this data no problem. 6 and 9 are linearly separable. Now, if I talk from 0 to 9, what are the two digits? Those are quite similar kind of shape. So if I say you 3 and 8, because 3 and 8 are having something similar kind of structure. Okay, especially in the right side. Okay, they are having these loops. In 8, I am having complete loop. In 3, I don't have this loop in left side. So let us say what kind of clusters I am having for 3 and 8. So again, I am putting PCA. Yeah. So you can see now 3 and 8 are not that much separable. They are having some sort of mixing. You can see it. Okay. They are not linearly separable. They are not having complete separate cluster as it was in the case of 6 and 9. Similarly, if I see 1 and 7, so you can see 1 and 7 are almost linearly separable, but since 1 and 7 are having something common kind of thing, so they are more close. So in that way, I can visualize my higher dimensional data using PCA. Similarly, I am having this iris data set, which is very popular data set for machine learning. Here we are having 150 flower samples from 3 different flower category. That is Setosa, Virginica, and versicolor, and it is a 4-dimensional data. So for each iris, what I am having petal length width, sepal length, and sepal width. These 4 features are there. So if you see this data I am importing, and then these, as I told you, these are coming from 3 classes. So let us say class 0, 1, and 2. 0 for Setosa, 1 for Virginica, versicolor, 2 for Virginica. And if you see this data, what kind of data I am having, I will show you. I restore, and I think it will work. Okay, no problem. Okay, it is data frame. So you can see here plain text for some data. You can see the data. So you can see it is a 4-dimensional data. For first sample, I am having 5.1, 3.5, 1.4, 0.2. For second, it is 4.9, 3, 1.4, 0.2. So in that way, I am having these 150 samples. Now I have to apply PCA and let me see, because it is a 4-dimensional data, you can see. I cannot plot it. But what I will do, I will apply PCA on this data. I will reduce the dimension from 4 to 2. Let me do it and let me plot this data. So you can see these 3 classes I have. So this purple class is almost separate from other 2 class. There are very small mixing in the clusters of rest of the 2 class samples. Okay. So in that way, I can analyze my data. Similarly, if I go to this wine data, which is again a 13-dimensional data, and again 3 types of wine from different vineyards of Italy, and there you are having 13 feature vectors and something like 178 patterns, 178 samples. And let me apply PCA. So I have applied PCA. I have reduced from 13 to 2. And then I am plotting it, that you can see. Now you can see the data are having mixed clusters. They are not linearly separable. But in original 13 dimensions, this data is linearly separable. So sometimes when you are reducing your dimension of your problem, the problem is easy, means linearly separable in higher dimensional space. But when you apply PCA and reduce the dimension, the problem may not be linearly separable. So that is one disadvantage of PCA. Okay. And here PCA will not work when non-linearity is involved. So for that, what we are having certain non-linear dimension reduction techniques, and those are called manifold learning. So one simple sort of manifold learning we have seen, which is PCA. And now we will focus on more advanced schemes. So manifold learning is an approach to nonlinear dimension reduction, because PCA will not work everywhere. When your data is having nonlinearity, then PCA will not work, and there you have to come with manifold nonlinear techniques. Okay. So what these manifold learning techniques will do, it uncovers hidden patterns or relationships in data. Moreover, it helps to represent the data in an accurate and meaningful way. We will see some demo. What is the meaning of this meaningful way? So first, let us learn what is manifold. So any object which is nearly flat on a small scale is called manifold. Like this line, it is a one-dimensional manifold. Now you are having this ellipse, but if you unfold this ellipse, what you will get? I will get a line. So it is again a one-dimensional manifold. You are having this curvilinear shape, but if you unfold it, you plate it, it will become again a line. So all these are one-dimensional manifold. Similarly, if you are having a piece of paper and I am having this kind of shape like this. So it is a three-dimensional shape, you can see. But if I unplate it, it is a two-dimensional, it is a plane. So it is a 2D manifold. Similarly, all these shapes are 2D manifold. Even our Earth, okay, which is a sphere, is again a manifold. You can, if you unfold it, it will become a plane, and that we are filling. Even though these are very small structure, and here you are seeing these non-linearity, curvilinear, or this kind of higher dimensional filling here. But like the best example to understand this manifold is Earth. Actually, in reality, Earth is 3D. But what we are feeling it in a local neighborhood, how Earth is look like, what we feel in local neighborhood, what we feel, what sort of Earth is. It is a plane in locally it is a plane. So it is again a very good example of manifold. Again, this is another very beautiful synthetic example of manifold, which is called Swiss roll. Okay, it is a three-dimensional structure. It has been rolled at different color points, cloud, and it has been rolled. So it is in 3D. But if you unfold it, okay, you plate it, you will get this kind of structure, 2D. Okay, so in general, a d-dimensional manifold is a part of n-dimensional space where d is less than n that locally resemble a d-dimensional hyperplane. Another example like this. So even though this surface is in 3D, but locally if you see it, it is just a flat surface. It is a flat surface. Okay, not that curvilinear. So what is manifold learning? Manifold learning is to learn the relationship between these two. So that instead of using this higher dimensional data, we can use this lower dimensional data. So to find out the best representation of this high dimensional data in low dimensional space, that is called manifold learning. Now, why not PCA? PCA is a linear method we have just seen. Okay, it is a matrix based transformation, and matrix is linear transformation. So what is the limitation? It fails to find the nonlinear structure in the data. So for example, if I apply PCA on this Swiss roll, you will get this kind of result. But is it really true? If I ask you, what is the relation between these blue points and these points? So they are having on the different ends, okay, extreme ends of this roll. But here you can see they are coming very close. Even some green points are far away from these blue points compared to this. But in originality, they are far away. So we are not able to capture this nonlinear structure of our data in low dimensional space if we apply PCA. So there are certain algorithms in manifold learning, and many more are coming, because still it is one of the popular research area in machine learning, although it is not that much popular, because it is a bit difficult to come up with new kind of manifold learning techniques. But one of them is multidimensional scaling. So this multidimensional scaling is a method used in data science to visualize and compare similarities and dissimilarities of high-dimensional data. What PCA do? PCA minimize dimensions by preserving covariance of the data we have just seen. Because using the covariance matrix, finding the principal eigenvector, we are preserving the covariance of data. Whereas multidimensional scaling minimizes dimensions by preserving distance between data points. Okay, so it will preserve the distance between the points of your data. So whatever distance you are having in higher dimensional, it try to preserve it in low dimension also. So for example, in high dimensional, you are having the maximum distance between this blue and this what I will say maroon point. So in low dimension also, it will put them far away. So that is the objective. Okay. So if covariance becomes equals to Euclidean distance, then PCA and MDS will become the same thing. Okay. But PCA use covariance. So very simple answer. Whenever you have to explain MDS, PCA use covariance, preserving covariance, whereas MDS preserving Euclidean distance. And how it will preserve, let me show you, means I am not going in these formulas. Because it is based on some minimizing some stress, which is defined based here. DIG is the distance in original space, higher dimensional space, and we find a representation in lower dimensional space, so that this DIG should be equals to delta Ij in the new lower dimensional space distance for all the points. Okay, but I am not going into this. Just let me try to explain it visually so that it is more. So this is a three-dimensional data. And here I am having 4 points, A, B, C, D. So let us say coordinates of A is x1, x2, x3. Coordinate is y1, y2, y3. C, z1, z2, z3. So in that way, you will be having these w1, w2, w3. And you know then how to calculate Euclidean distance between any pair of points. This Euclidean distance between AB will be nothing, just square root of x1 minus y1 square plus x2 minus y2 square plus z1 minus x3 minus y3 square. So you will be having this kind of thing. Okay. Now MDS, what it will do, it will project it into 2D. Let us say I am projecting it into 2D in such a way that this distance will be preserved. So like here, which point is closer to A among B, C, D? It is B. So here also in lower dimensional space, this B is close to A compared to, and which is the far away from A? Farthest? C. So here again C. So this kind of pairwise distance is preserving in lower dimensional space, and that is multi-dimensional scaling. So for example, here this was the distance in 3D. Distance between A to A is 0. D2A is 1.69, C2A is 2.53, D2A is 2.20. And why I am not completing this matrix? Because whatever distance you are having A to B, same you will be having B to A. So whatever entry you are having here, that will come here. So I am writing in this way only. And this is after applying multi-dimensional scaling. And so you can see it was 1.69 in original dimension, in reduced dimension it is 1.71. So whatever other projection you take in 2D, it will not be less than 1.71. 2.53, 2.53. 2.20, 2.20. So in that way, we are having this kind of thing. Another problem, here I am having this certain number of features, their distance between them, and this is two-dimensional representation. So if you see here, the distance between 445 and 434 is the minimum one. If you see all the entries, 0.14. Here again, you can see 434 and 445 is the closure one. So in that way, I will be having a lower dimensional representation of high dimensional data just by preserving the pairwise distance. And this is called multi-dimensional scaling. How to implement it? In Python, you are having a class scalar.manifold, and you are having this utility MDS. So you have to import scalar.manifold.mds, and when you are defining it, number of components means what dimension you want to the projection dimension in which you want to project your data. Then you are having some hyperparameter like number of initialization. So it will initialize this optimization algorithm because it is an optimization problem in the sense because whatever distance you are having in higher dimension, the same you want to keep in lower dimensional space. So you are minimizing the difference between those two. So different number of initialization will be done, and then what will happen? Whatever be the best result, that will be taken. Okay. Maximum iteration, because that optimization will be done using some iterative algorithm. How much error is permissible and what kind of distance you want to use. So more popular one is Euclidean, and that is by default also. So very easy implementation. But the second thing here, it is a problem. What is the problem? Problem is something like this. So let me explain here. Suppose you are having this kind of manifold. Let us say this is point X, this is point Y. So it is a one-dimensional manifold because if you plate it, it will become a line. Now I'm having 2 points here. One is A, another one is B. On this curvilinear structure. Now what is the Euclidean distance between? And then I am having a point, let us say C. C is here. So which point is close to A, B or C? If you talk about manifold in terms of manifold, after plating it, unplating it, plating it. So what will be the, which one will be the close to A? Because if you unplate it, it will be a line like this. You just X, Y. Okay, you have just stretch it. And then let us say this is your A. So which will come first, C or B?
C will be closer. C will be closer.
C will be closer. And then B. Okay. Now, if you see this Euclidean distance way. So what is Euclidean distance? In terms of Euclidean distance, A is close to B or C? Euclidean distance will be the shortest distance between 2 points. So between A to B, this is the distance. Between A to C, this is the distance. So which is close to A, B or C in terms of Euclidean distance?
B.
B. So when you go directly with Euclidean distance, if it is a plane surface, there is no valley, jump, or let us say hole in the surface, or as abnormality in the data, that's fine. But in real sense, Euclidean distance is not a good measure because it doesn't give you a correct picture. So preserving Euclidean distance, which we are doing in MDS, is not a correct choice because if you see these, let us say I am having 2 points on this circle. One is this one, another one is this one. Actually, what is the distance between these 2 points? You have to move along the surface of the curve. Yes or no? Like your
Yes.
aeroplane path. But Euclidean is this one. So Euclidean distance doesn't give you correct picture of the data. Similarly here, if you see the distance between these 2 points, Euclidean is this one. But originally if you unflat it, it's this one. So what is happening? Euclidean is not a correct choice. Even from this you can see. I am flattening this circular shape, and then I am showing you this is the Euclidean distance. But the actual one is you unflat it and then see. So this will become the distance really. So such kind of distance is called geodesic distance. Okay. Euclidean is, suppose I want to make it in 1D. Euclidean is you project onto a line and then you measure the distance. So this is the distance between A and C. But geodesic is this one. Okay, you unfold it and unfold it and then measure the distance. In that way, what isomap do, instead of preserving the Euclidean distance, it preserves the geodesic distance. And hence it is more accurate than the multidimensional scaling. Okay. That is the basic difference between MDS and isomap. Okay. And then again, you can implement it in the same way. Scalar.manifold.isomap, number of components, eigensolver, maximum iteration, tolerance, and so on. These kind of hyperparameter. The most important one is this one. Number of components, how many you want to keep. I am going to discuss only one more, this manifold learning technique, which is again an improvement of multidimensional scaling. So in multidimensional scaling, okay, you are preserving the Euclidean distance. Okay, it is good if the non-linearity coming in terms of simple operations like rotation, translation, and scaling. But when you are having complex kind of non-linearity, then this MDS is not able to capture the hidden structure of the data in lower dimensional space. So the solution is locally linear embedding. So what MDS is doing, if you are having, let us say, 10 data points, it is preserving the distance for all those pairs, for all pairs of data points. But what local linear embedding do, it will preserve the distance only some local, in the local neighborhood. So for example here, if these are the data points in 3-dimensional space, so it will select some local points, like these are those points, and it will preserve the distance of xi from all these points. to project xi into lower dimensional space. It will not take all those points into consideration, which was the case in MDS, multi-dimensional scaling. Okay, it will take some local points, and that is more realistic if we see. Okay, so that is the improvement of local, another version of MDS, which is called locally linear embedding, and that is the main difference. So we have seen three types of these techniques. One is multidimensional scaling, which preserve the Euclidean distance. The second one is isomap, which preserve the geodesic distance. And the third one is locally linear embedding, which preserve the distance only for locally neighborhood points, not for all the points. Okay, so these are some popular manifold learning algorithm, and let us see what kind of structure we are able to explore using this kind of technique. So just let me give you a demo of it. Second. So let me go first this demonstration, and it is coming from the problem of face recognition. So what I am having, we are having a famous data set which is called LFW people data set, LFW face data set, level face wild data set, LFW stands for. So what I am doing, I am fetching some of the faces of famous personality from this data set using this particular function fetch LFW people, and in this way I am putting a condition that for each person I should have at least 100 faces, face images. So these are face image only. So if I run it, you can see I am having total 1140 images, and each image is of size, I cannot recall correctly what is the size, but the total number of pixels in each image is 2914. Okay, 2914. So 2914 is the total number of pixels. So this data is 2914 dimensions. This much feature this data is having originally. What we will do, we will apply these manifold learning techniques on this data, and we'll try to explore some hidden structure of the data. Okay, so let me run it. These are just some sample images. So I'm having these kind of face images. You can see images of George W. Bush, Colin Powell, Rumsfeld, all those famous personality. Okay, okay. Again, George W. Bush. And in this data set, for each person, we are having 100 images. Now, let me apply PCA onto this data. And since original dimension is 2914, I will apply PCA. I will reduce it to 100 dimensions. Instead of 2914, I will take 100 principal components, 100 principal component features, and we'll see how much information about the variability of the data I can preserve. Just reducing dimension from 2900 to 100 only. So you can see. This is a commutative variance. So you can see on the x-axis I am having number of principal components, whereas on the y-axis I am having commutative variance. So commutative variance is like somewhere more than 90% for these 100 features only. So what you can say, originally I am having 2900 features, but only 100 features are having information more than 90%. Hence, many of the features are many of those dimensions or features are useless. Okay, no problem. Now I will apply isomap on it. Okay. So for applying isomap, as I told you, you have to import scalar.manifold, and from there you will import isomap, and you will give number of components in isomap, and then you will apply this fit and transform function. That is the basic way of applying any machine learning techniques in using sklearn, scikit-learn in Python. Whatever technique you use, whether it is a clustering technique, supervised learning technique, or unsupervised learning technique, or any other deep learning, you have to make use of this syntax only. Very few lines. So that is the beauty of Python, especially in case of scikit-learn. The implementation of any algorithm is same. If you know the implementation of one algorithm, let us say support vector machine, you can apply any other. Only thing you have to change the name of that. And you have to know about the what sort of hyperparameters are there for that particular model. So I am applying isomap. It may take some time. But yeah, it has been done. Let me plot the result. Okay. Yeah. So now this is the data in 2D. Let me make a bit small image so that you can see everything and you can find out what kind of structure I can. Yeah. So this is the projection of that 2900 dimensional data to 2-dimension. And what are those 2-dimensional features? Those features are your isomap features. Now tell me what sort of structure, hidden structure you are able to find out here. Tell me something, whatever you can observe from this visualization. What sort of features I can extract based on the information which I obtained using this isomap. So one of them is you go from this. If you go from this corner, top right corner to bottom right, bottom left, you can see the or you are going from right to left, you can see the illumination. Yes or no? As you are going from top right to bottom left, the images are becoming more and more brighter. Okay. So that may be one of the feature, one of the hidden structure which we are able to extract. So in that way, one can say that brightness is an important feature because image is not having uniform brightness and hence it can be utilized. Another one is if you see most of the images in bottom side, okay, in the down side, what is the orientation of the face? And then see the picture in top. What is the orientation of the face? Here it is orientation towards
left.
Towards left or right?
Towards left.
Yeah. And here it is towards
right.
Yeah. So that is another important structure we are able to. Okay. So in that way, one can find out a certain information about the data, hidden structure about the data, which one cannot utilize in a very raw way using any other technique. And in that way, this manifold learning is somewhat very important to learn. Okay. And it is very much applicable to real cases, use cases. Another example, let me show you very simple example. I am able to make it. Yeah, so that again the digit data set. And here I am having only, instead of all 10 classes 0 to 9, I am just giving you a demonstration by taking only 4 classes. So my classes are 0, 1, 2, and 3. So 0, 1, 2, and 3. So these are 4 classes I am taking. And then you know that it is a 64 dimensional data. Okay, 8 by 8 images. So what I will do, I will reduce those 64 dimensional to 2 dimension. And these are the, if you see here, these kind of handwritten characters I am having. 0, 1, 2, 3, these kind of. So these are some of the images from the data set. So it is a means cluster of images, cloud of the images. It is not complete a single image. Each image is having a single text. So 8 by 8 image, you can see very small. First, I am applying PCA. I am applying means I am reducing dimension from 64 to 2. And I'm projecting to 2-dimensional space, and then I will see what kind of data I am obtaining in 2D. Yeah, so you can see after applying PCA, this is the data. So what you can see here is this data is linearly separable by applying PCA and making the projection. Yes or no? No, you can are having mixed clusters. 2 and 3 are mixing. 1 is also mixing with, and then 0 is having somewhat different. And that is obvious. 2 and why 2 and 3 are mixing? Because 2 and 3 are having similar sort of shape. They are more or less similar kind of. 2 and 3 are having similarity, so they are more mixed. 0 is different from 2 and 3 in terms of shape, so they are separate, and so on. But what we are observing that we are not getting very good representation in 2D because we are getting the mixed cluster, and now we are having we have to use some complex classifier to classify this sort of data, which is having this kind of mixing. We cannot use simple linear models. What I will do now, I will apply local linear embedding as well as isomet. And then I will compare my result with PCA. So now I am applied both of them using the same command which I told you. In local linear embedding, I am using 10 neighbors. And then I am making this visualization using PCA, local linear embedding, and isomet. Yeah, so this is PCA, you know, it's kind of thing we have just seen. This is when you are using local linear embedding. So now you can see how separate is each class data in this way. These are more or less linearly separable. Yes or no? I am having a separate cluster for 0, separate cluster for 3, and separate cluster of 2. Basically, 3 and 2 are having similarity if we see from PCA point of view, and that's why they are merging. They are having a mixed cluster. But when you are going using some non-linear technique, it is extracting, it is exploring some hidden structure. And that's why we are getting separate, well separated cluster of 2 and 3. And similarly in case of 1 and 0. It may happen your 1 is written of two different way. Because some people written, if I go here, this one can, some people written one like this, some people written like this, some people written like this. Okay. And even though if you see in your data also, if I can go here. Yeah, you are having different kind of one. For example, this one and these one. One is having simple vertical lines, whereas in some cases you are having this on the top, this kind of corner. Okay. And that's why your this, what I will say, isome, which one is this one? Yeah, local linear embedding is able to explore this kind of thing also. No, yeah, one is there, but one is also written in two different way in your data. I am not seeing any even a single image from the data, but I am able to extract, I am able to get these kind of uh, information also, that I am getting two separate cluster of one. It means one is also written in two different way. If I am getting 4 also here, let me take one more, and then they are well separated, and this is the result of isomap, which is more or less similar to uh, one second. So, isomap is here, locally linear embedding is here. Oh, sorry. Isomap is xmds. So let me make it xis. Sorry. Okay. And then here also I am writing xis. Yeah. So this is PCA. It is running for LLE. Yeah, this is LLE. Sorry. And whatever we have, isomap is able to find out that also, that one is coming two types. And then local linear embedding is now coming like this. Because again, it will depend on how many neighbors you are taking. Here I am taking how many neighbors? 10 neighbors. Let me make it total 64 patterns. So let me make it 25 and let me run it again. Yeah, so you can see again it is a bit linearly separable. So in that way we are able to find out all those hidden structure of the data using uh, these manifold learning techniques. If you go this Swiss roll example using some synthetic data, so I have created this Swiss roll which is having 800 points, and you can see these points are coming from different classes represented by different colors. This is a two-dimensional manifold because it is rolled in 3D. If you unfold it, it will become a two-dimensional plane. I am applying PCA first. So after applying PCA, I am getting this result. So it is the real unfolding of your data. Tell me, is it real unfolding? No. It should come a plane. You have to unfold this Swiss roll. Okay. And PCA is not able to do it. It is just taking a projection of these points. It is taking a projection. Then you apply MDS. So PCA is using covariance. MDS will use Euclidean distance. So as you know, Even in this case, this is a rolling kind of thing. Here, MDS is also not a good choice because it will preserve the Euclidean distance. What sort of thing you need? You need here which preserve the geodesic distance, or just go with local linear, just preserve the linear Euclidean like LLE or isomer. So in case of MDS also you are getting this kind of result, which is again not a good one. Okay, but it is just preservation of Euclidean distance. Now come to isomer. Yeah, this is isomer, and you can see now we are able to unfold it, unfold the structure. And then I will be having local linear embedding. It will come like this. So again, it is what we will say, able to unfold it, not only unfold it, also from the inner side, it is having a width, whereas as far it will go, distance one, it will become, width will become less and less. So these are some demonstration of this, what I will say manifold learning technique. Okay. And now you are having a bit idea of this manifold learning technique. You can explore more literature related to it. You can apply these techniques in your problems, even though some problems suppose you have done by using PCA or any other linear techniques, then you can try these kind of non-linear techniques. Okay. So I think that's all from my side. Now I am open for any sort of questions which you are having. Let me see in chat window.
Thank you, sir. Participants, you can write down your queries in the chat box, or you can also raise your hand so that we can unmute you. Sir, we have one query. What
Yeah,
are the limitations of LLE techniques?
yeah, there is again limitation for everything. So as you know that, suppose I am having a data like this. Suppose I am having data from two classes, and data is something like this. Suppose this is the data from one class, and then I am having data from another class, and then again I am having some data from this class here. Yes. So now when I will come to lower dimensional space and I will apply LLE, so it looks only local, it will preserve the local distance. So again you will get a separate cluster of these two. Okay. So although what should be an intelligent technique, it should take make in the lower dimensional space. When you are going to new dimension, it should come with a single cluster because they are from the same class. But LLE again is not able to what I will say, capture this particular kind of scenario, which is very rare. But
Okay, thank you, sir, for such a nice explanation. We have one more query. Can you please give one more example for dimensional reduction?
which one?
Dimensional reduction.
Yeah, all those are dimension reduction only. I am reducing whatever be the dimension 2900 or 64, or I am reducing to dimension 2. You can reduce to 10, 15, 20. You have to change number of components only. Or is there something else? One want to ask, because it is not clear.
Any other query? Any other query from the participants?
Means exactly what they want to ask.
So can we use PCA for like 1 or 2 dimensional only, or it can be used for higher dimensions as well?
Any dimension n from coming to n to m, where m is less than n. N can be anything, 1,000, 20,000, 1 million, 10 million, 1 billion. M can be anything, but less than n. Okay, not just I have given you example of 2D or 1D because that we can visualize. We can have a feeling. If I am coming from, let us say, 1,000 to 20 dimension, then I cannot plot this 20 dimensional data. So nothing will come out. All those are unsupervised learning only. I never use the class information, whether it is PCA, ISOMAP, LLE or MDS. All these are uh, unsupervised learning. So any method to convert for supervised learning. Okay, you want to make use of class information also. Yeah, that is very nice idea. But how to use class information? Okay, let me give you. So there is a thing about linear discriminant analysis. There we make use of class information also. That is a sort of supervised learning technique, and you can explore about LDA from my YouTube lectures. There is a course of essential mathematics for machine learning. There I am having these lectures of LDA, and that is a supervised learning technique. And then corresponding to that, we are having kernel LDA also. Kernel discriminant analysis. So those are dimension reduction techniques where we are making use of class information also. Yeah, I am on mute.
Thank you,
Are you
sir.
able to hear? Gagandeep?
Yes, sir, we are able to hear you.
Yeah, so kernel discriminant analysis you can explore. I have not taken it in this lecture. These are supervised techniques for dimension reduction, where you can reduce the dimension and same time you can use them as a supervised learning classifier also in the reduced dimensional space.
Good evening, sir.
Yeah, please.
Yeah, sir, actually my thought process was LLE is for unsupervised learning. Can we do some identification or some classification sort of thing in LLE so that it can be also used for supervised methods?
Frankly, honestly speaking, I don't have the idea whether we are having this kind of thing. If it is not there, one can try to develop some new algorithm. Okay, but honestly speaking, I don't have idea whether we are having such kind of LLE version. But since we are having techniques for those kind of thing also, like I have given
Supervised,
you
we
an
have
example.
different techniques that I know. But just after listening to your lecture only, this thing clicked in my mind. Can we convert it
Yeah,
or something?
so that's why I am saying, means I don't have idea because I have not come across such kind of thing. But
I think if
if
I'll get into something, then I'll connect with you once again.
yeah, sure. Or else you can try to make it, or since you have given this idea to me also, so I can also try and I can publish something. Thank you for that.
Yes, sir. Thank you, sir. Thank you so much, sir. I think I'm done. Thank you. Thank you. Thank you, sir.
Thank you, Dr. Gagan. Anyone else? Okay, so let me give you just a brief this one. So even though if anyone want to have something further, so one can visit my website from here. So I am here with Department of Mathematics, as well as we are having now a new Center for Artificial Intelligence and Data Science at IIT Roorkee. which is having MTech and PhD programs at this moment in AI and DS. And again, I am a part of that also. So, and you can find more details about me in my website, which is faculty.itr.ac.in Malik FMA. Okay. So, what sort of research projects or about my publications, you can see details here. Okay. So with that, if there is no more questions, then we can
All the
close.
questions. Yeah, yes, sir. We can
Hello.
close now. Yes, sir.
Yeah.
We can close now. We don't have any other question from the
Yeah,
participants.
thank you. Thank you very much.
Yeah. Thank you so much, sir, for such an
Thank you.
informative session. We
Thank
all
you.
are thankful to you
Thank you.
for
Thank you.
enlightening us by your
Thank you.
knowledgeable
Thank you.
words. Thank you, sir.
Okay. Thank you. Thank you very much. Thank you all of you for listening. Thank you very much.
Thank you, Sanjeev, sir.
Thank you, everyone. With this session, we come to an end of the 1-week online AICTE training and learning faculty development program on the foundation of data science and its application. Now, I would like to hand over to Professor Nidhi Goyal, Head of Department of Electronics and Communication Engineering at Indira Gandhi Delhi Technical University for Women, to present the vote of thanks. Over to you, Nidhi, ma'am.
Thank you. Thank you, Sakshi and all the organizing team members. I would like to thank all the participants for a patience listening for the last 5 days. And at the end, I would like to thank all my organizing members who has handled all those 5 days with such a grace and a patience. They were readily available to handle the sessions in the morning, afternoon, evening, and at the same time, you can see you have been getting responses at your WhatsApp or your Gmail group in case any query has been raised. So I personally thank Ms. Neha Kapoor, so all of them, they have contributed a lot, and I believe with the hand attendance will be taken from the Cisco WebEx. You are supposed to give the test. Portal, because without these 3 conditions, attendance, feedback, and test, we will not your certificate will not be generated at the portal. And in case of any query, you can just speak to us. That's not an issue. Send a mail or drop a WhatsApp group. It will take almost
Ma'am, we can't hear you.
Yes, ma'am.
your ATAL portal. You have to put in your login details on the ATAL portal. You will get the feedback link over there. I hope that solves all the doubts. I think we can leave now, and thank you everyone. Thank you my team, and thank you all the participants. Thank you. I think there are network issues. I should switch off my video. Thank you to my team. Thank you to all the participants, and thank you to the ATAL FDP, ATAL Academy. for sanctioning this FDP so that we can share, the knowledge with you. And I can see a lot many thanks to the organizing team members. Apart from me, the participants are also thanking Neha, Anushri, Palak, Sakshi, Archita, to everyone, because they have working hard since last 5 days. Thank you all.
Thank you, ma'am. So we hope that all the participants have learned a lot from these sessions.
There is a very good comment in the chat box. They're saying it's a women's show. Yeah, it's a women's show. We are a women's university, and we do wonders not only in organizing this FDP, but organizing many events and in competitions. Thank you. Thank you, Anushri. Thank you, all the team members. I would like to leave because I was in the middle of a meeting. So I thought of, just give a vote of thanks because my team has been working hard since last few days. Thank you. You can formally close the session now.
Sure, ma'am. Thank you so much, ma'am. So we hope that all the participants have learned a lot from these sessions. We are very grateful to all of you for your enormous cooperation and the time and effort you took to come, collaborate, learn, discuss, and share your knowledge with each other. Thank you so much, everyone, for being such wonderful participants that participated enthusiastically throughout this week. We look forward to having you again. Thank you so much, everyone. Thanks a lot.